Thank you. Hopefully, the copy of my running copy of my notes, which is typo-filled and things, but as I write them, I'm going to put them on the website. Hopefully, the version from this morning is going to go on the website. But my guess is you might want to load them onto your computer, but not print them. Wait till it's sort of finished before you actually print these things. But it's there in case you want to refer to it as we go along. So we were looking at chordal SLE. And last time we discussed the existence of the curve, which we proved for capital not equal to 8 modulo an estimate on the derivative. So I'm letting ft of z be gt inverse of z plus ut. And what we're interested in are estimates. Well, we're interested in probabilities, but to get probabilities is standard ways to get estimates. So hopefully you're convinced that we're interested in computing moments for that. Now, when computing moments for the derivative, it turns out it's useful often to look at the reverse Loebner flow. So the reverse Loebner flow or reverse Loebner equation can be thought of as the Loebner equation run backwards in time, negative time. So in this equation, points here move toward the real line. Their imaginary part decreases over time. Here, the imaginary part increases over time. And in fact, in this case, the solution to this exists. So if z is in h, again, we start with h0 of z equals z. And then solution exists for all times, for all z in the upper half plane. So in this case, so ht is a conformal map from the upper half plane into a subdomain of the upper half plane. And the relation between these two is given by an exercise. And whenever exercises are given, one of the parts of the exercise is to figure out what are all the appropriate typos in the exercise. And Brent, who's going to give the tutorial tomorrow, claims he's worked out or at least he thinks he's figured out the typos in this exercise. So I'm going to state it the way it should be stated, not the way it's in the notes right now. Okay. Suppose GT is a solution to star. And HT solution to double star. Where V sub t is u of s minus t minus us. And both of these solutions I'm only doing from time 0 to time s. Then us plus hs of z equals fs of z plus us, where again fs is given by this. So this is just a deterministic fact about it. Yeah. Oh, right. Sorry. Fs of z. Yeah, thank you. Now, in particular, so this is deterministic, and leaving this as an exercise. So if we fix an s, and if u sub t, 0 less than or t less than or equal to s, is a standard Brownian motion, then so is Vt. Hence, what we have is the following sort of corollary. If GT is solution to star with UT a Brownian motion, and HT solution to double star where VT is a Brownian motion, then UT plus HT of Z actually, let me put this over here. And HT of Z has the same distribution as FT of Z minus UT. And HT prime of Z has the same distribution as FT prime of Z. Right, take the derivative, that UT doesn't have a Z in it. Now, what I want to caution you here is that this is a fact about one particular time. It's not a fact about the joint distribution. So if I looked at this quantity for 0 less than or equal to t less than or equal to s, and this quantity for 0 less than or equal to t less than or equal to s, they would not have the same joint distribution. This is a distribution at one time. Just sort of a picture. When you're doing the sort of forward Loebner equation, what happens on the far side, you can sort of think of the picture as this. You're growing it like that. But basically, if you're going to grow this curve, you start by growing this, and then you grow that. For the reverse equation, what happens is, if I'm trying to grow this curve, what I start with doing is I grow this part first in the reverse Lerner flow. And then I keep growing the curve at the point here rather than at the tip, and I push it forward. So the times are different here. However, if we're interested in, say, distributions having to do with this, the reverse flow works fine. And as we'll see later, though I don't want to emphasize it right now, you can also use the reverse flow if you're interested in joint distributions at f prime t, f prime s. Yeah? Yes, this is a fact about the function. So the function ht has the same distribution as the function ft minus ut. Yeah. Sorry, thank you. So today we're going to be looking at this equation and concentrating on it. And similarly to what we did last time, I'm going to let Vt be minus a Brownian motion. If I have a point in the upper half plane, I let Zt of z, which I'll sometimes write as just Zt, and I'll write it as xt plus I yt. And it's ht of z minus Vt, or ht of z plus Vt. And then I know no way right around it, but we're going to just have to put up a lot of computations today. See, is there for a dry rag, if I can find one? And then I'm just going to put a bunch of computations, and then we can write that equation. Well, let's write in terms of x and y. dxt equals minus xt over xt squared plus yt squared dt plus dbt. And yt is differentiable in t, and it equals ayt over xt squared plus yt squared. So as we see, the imaginary part is growing with time. So we've got the equation over there. Let me just do a couple other. So if I differentiate with respect to z, I get a ht prime of z up top and a square the denominator, and the ht prime of z disappears if I take the logarithm there. So this is a over zt squared. And the reason to go through the logarithm is because what I really want is the absolute value of ht prime, and the log of absolute ht prime is the real part of log ht prime. So I can take the real part of this equation and then differentiate it. And get this. So this is just the Lerner equation, just the facts about the differential equation. And there are various forms of things that I'm going to be interested in. It turns out it's useful to let st be the sign of the argument of zt, just which is yt over zt. I'll write this way. And the one other quantity I'm going to call upsilon t, and that's ht prime of z over yt. Now, I've dropped the notation on this, the z, but it's important. All of these things here depend on the little z. They depend on the little point that we started with. I don't want to keep writing it. Same. So this also depends on the little z. And again, this actually is differentiable. This is, well, because these two are differentiable. It's just the chain rule. So one of the general exercises that won't be done in the tutorial session is check all the arithmetic and all these computations. So at some point, we have to do an Ito's formula calculation. And the way I've written is in terms of st. So yt is differentiable, but xt has the Brownian motion in it. So when I look at st, it has a stochastic part. And I'll just, so Ito's formula. R is a real number. You may not want to actually look at the, write this all down. There should be an xt squared. Okay. just little bits of tips when doing all these Ito formulas. It just takes a lot of calculation to do it. But it's generally useful in the long run when doing these things to write your answers in exponential form, which I mean is factor out the original guy in the rest of the stuff. It's going to be useful when doing the computations. Okay, now just a couple of points. Yt is like this. Another sort of nice way of writing this is dyt squared equals 2a yt squared over xt squared plus yt squared. And from this equation, you see that the derivative of yt squared, the way I've written it, is less than or equal to 2a. So we always have that yt squared is less than or equal to whatever my initial condition is. And it's always bigger than or equal to my initial condition. And here's the main calculation that I can't really motivate except just do it. Suppose R is a real number. Let lambda, which depends on R, be, remember A is A is 2 over kappa, so you can convert these to kappas if you want. I'm writing them in terms of A. And zeta is R minus R squared over A, or lambda minus R over 2a. So that's just the definition. Then if I let mt, and this depends on R and Z, but I'll make that just implicit, be ht prime of z to the lambda, yt to the zeta, st to the minus r. Is a martingale satisfying dmt equals rxt over xt squared plus yt squared mt dbt. Yeah. I think that's right. Oh, no, but it's okay. This is just a matter of algebra. Are these things equal? There may be a type. I'm sorry, you can't have. If this is. Is this 4a? Is this? Okay, this is just algebra. I'm going to leave this. Okay, let's. The first. R minus R squared over A. Is that equal to lambda minus? Maybe it's R squared. Maybe that should be R squared over 2. Okay. Okay, let's. Okay. There may be a typo in this. Okay. I don't want to really worry about the exact. Okay. One of the things, I'm not worrying about the exact values of these things at the moment. Over 4. Zeta should be R squared minus, there should be a 4 there. That's what I'm missing in my notes. Okay. The exercise is to notice all the typos I made in the notes. And you've just succeeded in one of the typos, in one of the exercises. Okay. But I want to comment a bit about this. This is just an Ito's formula calculation. Actually, the hard Ito's formula calculation was over there with the ST. This is really now at this point just chain rule or product rule, because 2 of these things are differentiable in T. There's only one that has a stochastic component. Okay. I do want to say a little bit of experience at this point. There's a tendency to show things are martingales and not write down the equation that they satisfy. I've gotten very much in the habit now, for all these martingales in SLE, to actually write down the equation in exponential form. When I say in exponential form, it means dmt equals, okay, exponential form, I mean something like this. AT, MT, dBT. The martingales we're going to be dealing with are non-negative. So this is an example. This is a non-negative martingale. So let's assume we have a non-negative. So non-negative m sub t satisfying so this is just a so getting this is Ito's formula. However, you cannot conclude from this that this is a martingale. From Ito's formula, you can conclude it's a local martingale, not a martingale. So this computation gives local martingale. So let me continue just sort of abstractly here. Now, if I don't let the process blow up, then it will be a martingale. So if I, let's say, tau n, okay, let's assume it's, I'm also assuming continuous, which means continuous paths, continuous local martingale. Let tau sub n be the first time that m sub t is bigger than or equal to n, or a sub t is bigger than or equal to n. And if I let mtn be mt min tau n, then mtn actually is a martingale. So if I have that, so this is often called localization or a version of localization from stochastic calculus. When one has a martingale, one can use the Gusano theorem. So Gusano is going to be important. So I want to say a little bit about this. So if MT is a martingale, and okay, when I say martingale, continuous and non-negative will be assumed. So all my martingales will be continuous, non-negative martingales. So if MT is a martingale, then we can define let's say martingales, let's say satisfying stars, or well, we can define a new process. New measure, new probability measure. And I'll use stars for this probability measure when I talk about it. By the probability of an event is equal to the expected value of the indicator of E times m sub t, if E, what I didn't say explicitly, and I should say, is the martingale is with respect to the filtration of the Brownian motion. So I've gotten about, this is assumed to be adapted with respect to the filtration of the Brownian motion. And whoops, that's not necessary. Have to divide by m0 to make it a probability measure. And what Gusano says is that there's a few ways of saying it, but that dBt equals AT dt plus dWt, where Wt is a p star Brownian motion. And AT is that thing that's in that equation over there. Okay. This is assuming MT is a martingale. If I just have an equation like this, I can't use Gusano without being careful. But I can look at this guy. So given local martingale, we can use Gusano on the stopped process. And then we get the same equation, is that dBt equals AT dt plus dWt, although at this point we just be careful that that's true for t's less than or equal to tau n. But the process AT doesn't depend on tau n. It's the same process. If I want to know whether or not this is actually a martingale. What really happens, what prevents this from being a martingale, is that when I wait by the martingale, I might blow up on an event, sort of expectation might concentrate on an event of probability 0 in the original measure. But that won't be an event of probability 0 in the weighted measure, because the weighted measure, to do this, if the limit as n goes to infinity, the probability that tau n is bigger than t is equal to 1, then in fact this is a martingale. So in order to check whether or not something's a martingale, a local martingale is a martingale for positive things, positive continuous local martingales. What you do is you can just use this Gusano transformation. The Gusano transformation tells you what the weighted process looks like, and if you can actually analyze the weighted process to answer whether or not in the weighted process things blow up or not, you can answer whether or not things are okay. P star, well, okay, it's a little fuzzy. P star, it depends on n only in that you have to take your BS T min tau n. So in other words, the Brownian motion up to tau n, but other than that, it doesn't depend on n. So it's a measure on stopped paths. But the drift, so basically the drift does it. So yeah, I mean, what's really here is, I mean, dBt is equal to what you really get here is AT indicator t is bigger than tau n. So as long as you have t is less than tau n. Yeah, that we haven't stopped yet. So you really need to replace it with that. But other than that, it's the same. So let's look at this particular case. So we have dBt is equal to rxt over xt squared plus yt squared mt. Oh, sorry, no, ignore that. dt plus dwt. To be careful here, okay, there's this implicit stopping going on over there for the time being. But for each n, this is stopped at some time n. I had the formula for xt, so dxt was minus a. Let me just drop some of the t's. dw, sorry. By the way, I'm not writing the equation for y. y is differentiable in t, so the equation for y doesn't change in a new measure. It has nothing to do with the measure. But there's an implicit equation for y in there. So when I do this, if I look at this equation, well, this drift, I mean, what we really have to worry about is, does x get large? Because I probably have lost them, but I won't write them down again. We have differential equations for ht prime of z, and these two guys, there are differential equations for them in terms of x and y. Just not SDEs, just deterministic equations. Y is bounded. You can actually show that this also stays bounded away from 0 and infinity in both directions, as long as x stays bounded. But x doesn't get large here in finite time. This is, say, bounded by a corresponding Bessel equation. We can just see that x doesn't, the distribution of x is tight in the weighted measure. Since the distribution of x is tight in the weighted measure, so are these distributions. And so you can just check that. Such a large board, I can't find things anymore. No, maybe. Well, OK, I can't. What we can check is that, in fact, there, that's what I'm looking for. We can check that this condition holds. And so all of that is really needed in order to convert the local martingale fact to a martingale fact. This is related very much to the fact that the reverse flow moves things away from the origin, which makes things nicer. We're going to see a similar martingale tomorrow on the forward flow, which will be a local martingale but will not be a martingale. So it's important to have the distinction here. OK. Let me put z equals I in here. So in this case, m0 is equal to 1 because the sign is equal to 1, the imaginary part's equal to 1, and this is the identity map. And therefore, expectation of mt equals expectation of m0 equals 1, because it's a martingale. Now, what we would like to say, so for the typically, by typically, I mean if I wasn't worrying about the fact that there's this ht prime in there, just with respect to the Loebner flow, yt tends to be at time, we tend to grow, the y component in time t tends to go, now t is going to be, now I'm going to let t go to infinity. Typically, yt is of order t to the 1/2. And typically, we're not skewed. Typically, the sign is of order 1. So we would like to say that we can't always say it, so don't, this isn't, but we can always like to say it if we want. So this gives a conjecture or maybe just say a question. By the way, an exercise I forgot to mention, which is actually very important. I'll back up and mention it. Exercise show that the distribution of ht prime, ht r squared prime of rz, or actually let me use a different letter than r. I use b. Here b is bigger than 0. Show that the distribution of ht b squared prime of bz is the same as ht prime of z. I forgot to mention that because, like for the original problem we were doing, most of the problems we're actually interested in this quantity where t is of order 1 and z is getting close to the real line. But now we're pulling z away from up to I. We're keeping, and we're letting t go to infinity. But this exercise converts the two. So. And the basic fact, which we're going to lead to today, try to get to, is that this relation is correct if r is less than some critical value of r. And the critical value of r is 2a plus a half, a 4 over kappa plus a half. What we're really interested, by the way, is relationship between lambda and zeta. We're interested in this kind of relationship. But it turns out when analyzing these things, r turns out to be a more useful parameter to sort of do your basis from. Then you can do your computations in lambda versus zeta. So this will correspond to lambda less than a plus 3 over 16a plus 1. And in this regime, we can actually write zeta as a function of lambda. And that's what we're really going for, but that's only for lambdas less than a critical value. So for the rest of today, I'm going to concentrate on R less than R critical. I'm going to look at this regime. And I'm going to let Q be 2a plus 1/2 minus R. And as we see later on, the critical fact will be that Q is bigger than 0. Okay, so we're interested how a process like this moves over time. There's really only one variable stochastic component. The only stochastic component is, well, then xt, or if you write the equation in for the st term. It has a stochastic part. The other parts are not stochastic, but you have to keep track of them. But yt grows monotonically. So one thing you could do, and this goes back to the paper of Roden and Schramm, is to change the time so that yt grows deterministically. I should say there's also, we had this upsilon t that, let's see. And we could also use that as a deterministic, but we're just going to use yt as the deterministic. So what we're going to do is imaginary part reparameterization. And now we have more computation to do. So let sigma t be the infimum of all times s. Okay, I'm going to do to ys is equal to e to the as. It just makes the equations easier to do it this way. So sigma t is the first time that the imaginary part reaches level e to the as. So the logarithm of ys is growing linearly. I'll put hats for z, x, yt hat, by definition, is e to the as. I'll also write ht hat and st hat for the corresponding things in the new parameterization. And I'm going to introduce two more variables. Yeah? Yes. And that is a typo in the notes. I was just reading for the notes, but yes, I do mean e to the at. Okay, so these are new quantities, so I won't bother hatting them. So kt is basically the x hat sigma. X, that's another typo in the notes. That should be x hat t. So y hat is e to the as. So xt hat is e to the as times something, and that something is kt. And yes. Okay. Thank you. Do I have any others? Yeah. Okay. Right. Sorry about this. And we'll define jt to be the inverse hyperbolic sine of kt. That just turns out to be the right variable to use. Well, jt is inverse hyperbolic of kt. Kt is hyperbolic sine of jt. I just wrote it. Okay. Okay. So now we have to do some computations. So now some more computations. Oh. So checking all these things. So these are just deterministic computations from this. Let me just focus on I. So those are deterministic computations just from the Lorger equation and for the nature of the time change. The following is a stochastic time change. So this is an exercise, but I'll just do it. I'll just say the computation. There is a standard Brownian motion, which I'll call BT tilde, such that dkt equals minus 2a kt dt plus square root kt squared plus 1 db tilde t. And jt is the one that satisfies the easiest equation. djt equals minus q plus r hyperbolic tan jt dt plus dbt tilde. So let me emphasize here, I'm talking about the original probability P, not P star here. So this is just for the Brownian motion. Let me let nt be the martingale at sigma t. By the way, if you start with a martingale and you time change a martingale, as long as you're not unlucky, you're going to get a martingale back. You can have some loss of mass, but that's not a problem here. This turns out to be a martingale. And I'm just going to add some more notation, sorry, but I'll explain why I'm doing this notation change in a second. Hardly seems worth writing all this up, but it's just. Okay, my reason for adding a little more notation here is that nu and xi can be written without an a in it over there. So now I basically have just the parameters r and q, and I've gotten rid of a. And this is a martingale satisfying dnt equals r tant jt dt whole bunches of calculations. Yeah? Is that a question, or did I say what? Oh, I'm sorry. No, I'm sorry. I skipped a step. Sorry. In the weighted measure, okay, so we are going to weight by the martingale n sub t. Basically, weighting by the martingale n sub t is the same thing as weighting by the martingale m sub t, just looking at different times that you're doing it. It's the same. Mt and mt are the same martingale. They're just time changes of each other. So in P star, in this time change, we have d bt tilde equals r tant jt dt plus, no, I'll say dwt, where wt is a P star Brownian motion. So what we're trying to do is look at this quantity. As a step toward doing this, we're going to look at the equivalent quantity in the time change. And the equivalent quantity in the time change is given by this. So we have expected value of e to the nu lt, e to the ct, so what's the purpose in doing all of this? well, here is my derivative hiding. I'll remind you, that's the derivative term over there. And what I'm really interested in is this. But what I have is the expectation of this. So what I need to do is find out what this looks like. So suppose E is an event. Depending on everything up to time t in the new parameterization. Then the expected value of, so this is n sub t. N sub t indicator E is equal to P star of E. So basically, in the new parameterization, that has turned into a deterministic. That's the YT has become deterministic, essentially. This is what was the ST term, has become this. And what we have to do is say that this is nicely controlled. So if I'm interested in saying, what's the probability that the cosh is no more than 1, or cosh is no more than 2, say, JT is no more than 2, I can just ask, what's the probability that at time t it's no more than 2 when dJt satisfies minus q tanh jt dt plus dWt. And now we'll work and see where q bigger than 0 has become crucial here. For q bigger than 0, this is a positive recurrent diffusion. So this is so I'm about to write down its invariant distribution, but I can't resist telling people, the quickest way in my mind that I compute these things from scratch, when I haven't seen these things, for a certain class of equations. This equation, so note, this is obtained by starting with JT as a Brownian motion, and weighting locally by the function f of x. In this case, it's it's cosh x. Cosh x to the minus So let me do a digression to explain weighting locally in the quotes a little more precisely. So suppose JT were a Brownian motion. Then an f or a function, dfjt is equal to f of jt times f double prime b jt. Well, okay, b is j. My notes have b, so let me. So that's just simple Ito's formula with the f of bt factored out. Or, yes, right there. Thank you. So mt equal to the exp of minus integral from 0 to t f double prime bs over 2 f of bs ds times f prime of bt over f of bt. Sorry, no, I'm sorry. F of bt satisfies dmt equals mt log f of bt prime, which is just another way of writing this, but I'm running out of room as I can't afford the denominator. dbt. So when I say weighting locally, it's like it's trying to take this as a martingale, but you always have to normalize to be probability 1. And this is kind of your local normalization. Compensator is often called to be probability 1. And then if I weight locally by f, capital F, is the same thing as weighting by this martingale, and this is often just a local martingale, but it's just using Gusano. So this puts a drift of log fbt prime. And hopefully, so that's. So now let me wave my hands a little bit, but I think it's a nice way of thinking about things. So now I've got a diffusion. And so let's consider just the transition probability starting at x and being at y at times t. So let's start with Brownian motion. So this is Brownian motion. And for Brownian motion, we have symmetry. Basically, if I have, roughly speaking, if I have any path omega, and I let omega r be the reverse path, they have the same probability. In this weighted measure, what you're doing is you're starting with the Brownian motion, but you're putting a weight on it. And this gives a Radon-Nikodym derivative. And there's a Radon-Nikodym, there's a term here which is somewhat complicated on each path. You have to integrate this along the path. But the key fact that I want to emphasize here is that whatever this is, if I take a path omega, the reverse path gives me exactly the same thing. So this compensator is actually invariant under the reversal. And so what you get is that in the weighted measure, and this is, okay, now this is now assuming not worrying about paths that might have died. And so this is assuming we're in a paths have not died. In our particular case, the paths live forever. There's no problem. We get ptxy equals ptyx, but you get f of y squared over f of x squared. And what you get is that invariant density should be proportional, should be a constant times f of x squared. That's the key fact. So for here, that's my drift, but my capital F is cosh x minus q. The invariant density is, in fact, constant cosh x to the 2q. So I'm not quite sure how much I'm going to get done, but the idea is that for a one variable SDE diffusion that's as simple as this, we can give very, very detailed information. For instance, let's go back to L sub t. So L sub t is t minus so jt is satisfying this. In our particular example, we were starting with j0 equaling actually, j0 equals 0 in our particular case, because that's the sin. So if I'm interested in what this looks like for large t, well, this is basically, well, that's t. But here, basically, say if I want the expected value of LT, it's equal to t minus of that ds. But we just have a simple positive recurrent diffusion. For large times t, it has this invariant density. So basically, for large t, all you have to do is find the expected value of that with respect to the large density, and you get that this, so limit as t goes to infinity, expectation LT over t equals mu And I'm calling it mu, but it's 1 minus 2q over 1 plus 2q. We also can say, at any large time t, we know what the distribution of this is with respect to this measure. And it's actually nicely tight around the origin. So in fact, this tends to come out. We can actually, we know very much about how this goes in things. It turns out when doing second moment estimates, and that's one of the reasons to be this careful. One doesn't need to be this careful when doing first moment estimates. It's for second moment estimates that the care is really very useful, that one can actually get more information. So let's so here, so we have this functional LT. So we would expect that LT is equal to mu t. And if things are nicely bounded, we would expect the random error to be of order t to the 1/2. And in fact, it is that. And in fact, we can actually get exponential bounds. So I'll just say what you can show is that if you look at LT minus mu t over t to the 1/2, maybe let's choose t at least 1. Let's not worry about it. Okay. And take an exponential moment of that, you can actually show, you can, actually let's make this absolute value. We can actually get this. We get actually very sharp bounds on this. For those who want to, the way that you get the exponential bounds is basically I have this martingale, which I've been thinking at a fixed value, for a fixed value of q or a fixed value of r. But if I vary this in a little neighborhood about r, then I get things as well, and I get this. So in fact, I actually can get that Ls minus mu s is around square root s for all. And this is in the weighted measure. So I want to sort of take an example. So the kind of event we're going to need, suppose E is an event of the form. Okay, so I'm going to want okay, I'll put the s plus 1 in there. So I want, okay, I'm not finished yet. I want this to be true, but there are fluctuations over time, and I can't get away with this. I don't want to be precise about the fluctuations, so let me put my good old subpower function c in there. And this is for all s between s and t. And actually, let me put a constant in here as well, even though I can. Okay, and I'm not finished with this event yet. I also want that Ls minus mu s is less than or equal to constant square root s plus 1 ct minus s. Okay, so this is, when one's really doing second moment estimates, one often needs things up to constants. And what this says is that ls minus mu s is up to a constant equal to the square root of s for s near 0 and s near t, but maybe somewhere in between. It's unfortunately we have to allow a little out there. Similarly, we want js to be less than or equal to some constant c of s, and maybe in js And just by analysis of one variable SLE, one can say there is a C. You can give it explicit C, but I don't want to worry about it. There's an explicit C such that if I consider the probability of this event in the weighted measure, let's just to play it safe, let's take a lim inf here. The lim inf of that. And now let's take the limit as c goes to infinity. This is equal to 1. You can be more specific than this, but this is the kind of flavor that you get. Now, everything I've done so far is in the, okay. Running a little short on time here. So what I've done here is I've taken my original problem on the reverse flow, moved it to this constant y, or this imaginary part parameterization. And now I'm looking at the imaginary part parameterization problem. When I'm looking at it at the time when the imaginary part gets a certain level, now I understand things very well. As long as this q is bigger than 0, I actually understand things very well. At some point, I actually want to convert to the other time, but here's the important fact. I'll remind you, sigma of t is the integral from 0 to e to the 2as cos squared js. Without being precise, on the event E, on ETC, this looks like e to the 2at, up to constants. This constant does depend on this constant c here. But when I look at when I'm looking at this guy, how much time has he spent? The bulk of this integral, because of this e to the 2as, the bulk of this integral is when s is of order t. When s is of order t, this is of order 1. There's no c in there. That's the reason to put this carefully here. And you can actually get that it's equal to this. And that's what allows you to convert from imaginary part parameterization time into this. Okay, there's actually a lot more arguments, but that's the basic reason. If we were not in the regime the regime R less than R critical, where Q was not, if Q were not positive here, then solutions to this would not concentrate around the origin. This martingale, the Cosh squared JS would get large. You would not get estimates like this. Estimates like this require that this thing to be concentrated near 1. And that requires Q to be bigger than 0. Okay. So what I wanted to show was let's put a t squared in there. I haven't finished the argument of this. I will tell you, if I continued this argument without much more, I could get one direction here. I could find a nice event E under which this holds. I would get a lower bound. The upper bound takes more work, and I don't want to do the upper bound, and I won't do the upper bound here. The same ideas come into it, but I originally only got the upper bound for some values of R, and then finally got the for all R less than R critical. I will say for the problem of yesterday's problem, this is much finer estimate than one needs, than Rode and Schramm needed. Rode and Schramm did not get estimates of anywhere of this precision, but they didn't need them either. Okay, now I won't bother to put formulas on the board, but because there's always a chance that they're wrong. But there were formulas for this. So now to prove the result from yesterday, all you need to do is plug in the numbers and check it. And if I started doing it on the board, it wouldn't work probably. But it's just plugging in the numbers. What I'd like to do is I just want to give one more exercise, and there's a typo in the notes on this one as well. And this exercise is one of the small pieces of showing the bound in the opposite direction. So parabolic that's a fancy word for a simple thing. So for every compact V is probably a bad letter because I'm using VT, but I'll keep it there, okay. So this is a compact subset of the upper half plane, which means it stays away from the real line. And every S naught bigger than or equal to 1 there exists a C such that C1 to the lambda expectation HTI prime to the lambda is less than or equal to expectation H prime STZ to the lambda less than or equal to C2 to the lambda expectation h prime ti to the lambda. And this is for t greater than or equal to 1 and s between s naught and 1 over s naught. So parabolic Harnack inequality is just a Harnack inequality where you have both a time and a spatial thing you're going on. Oh, z has to be in V. Okay, I think I'll stop there today.